Okay, so posted the next assignment with a few problems on topics we covered and we are covering now. In the first question, I've asked you to explore a little bit more about the ballistic transistor theory or model that we developed, and to also see some things to do with design of things like linearity and things like that. Meaning, if we have, we talked about the transistor as a device that, with the gate and the source and the drain. Typically, the circuit diagram may, look something like that. And typically, the transistor is not just used to as an electrical switch, right, which allows, for example, current to flow from the source to the drain based on, whether the gate allows it or not, right? So that the on and the off states of the device. It also has a very important. So this was the on and off. If you look at your drain current versus the gate voltage, in a log scale, it would switch by many orders, as you did in your assignment, and in a linear scale, it would look, something like that, right? And depending upon the drain voltage, and if you have a smaller drain voltage, it may look something like that. So at smaller drain voltages, ds, right? But then there is a sort of a threshold voltage which we talked about, right? Yeah, around which it turns on. So that's your on-off part of it. And the other aspect of it is in the gate, on-off can be done by either being, here or here, right? That's off, that's on. That's one functionality of the transistor. In fact, in most microprocessors, you'd get, zeros and ones, and then you can transmit signal this way. Let signal through or not. And by combining transistors, we do all kinds of logic things, NAND gates, NOR gates, XOR gates, and all that, right? So we're combining them together. You can also do logic by having switches, lights. Classically, you can do logic that way, or with billiard balls, whether a signal can go through or not. So that's classical computation. The other very important aspect of a transistor is, this gate. Instead of being applied, connected to a voltage, it can be connected to what we call as an antenna, in engineering terms. What that really means is, if you get your cell phone, the metal wrapped around the edges, that's the antenna, and that directly receives electromagnetic waves from air, and that's a metal. So the electrons in the metal are sloshed back and forth. And what that's doing is it's changing your gate voltage. Maybe you are biased here at, normally, and then because of this AC signal, the gate voltage starts oscillating a little bit. So, and then you can see that if that happens, your current will actually change by quite a bit. You see that, right? The current starts depending upon how much. This slope is called the gain, or the transconductance, right, GM, which is the derivative of drain current over VGS. Transconductance, because it's not drain current versus drain voltage. If it's ID versus VD, that would be just conductance. But ID versus VG is a third terminal, not in the path of the current. So that's why it's called transferred transconductance, right? And so higher is the transconductance, the larger is the swing in the output current. And the output current times maybe, there's some resistance here, it translates to output voltage. So the input swing in the voltage is amplified by the output voltage. So there's a voltage gain in this system, right? And that's the amplifier aspect of a transistor. It's slightly different from the digital switching aspect. And that's obviously a very important thing. In fact, some of the earliest uses of transistors were as an amplifier for transmitting telephone signals across the, from the east to the west coast and things like that in the US. And you needed amplifiers. This was done by vacuum tubes, and transistors kind of replaced them. And this is kind of the idea behind it. So you get a small voltage swing. Typically today from cell phone towers, this would be maybe in, I don't know, nanowatts or something like that. And you can calculate in nanowatts how much would be the effective voltage swing, and then the transistor can amplify it by a large amount. And there are other things like you filter out, there are filters and that signal, if you are receiving a 4 gigahertz signal, then you want to filter out all the other things. You don't want to amplify all the things that are noise as well, and things like that. So the first problem is kind of saying that if you have a ballistic transistor, the first part is just the current aspect, but then saying that if your gate voltage starts oscillating a little bit, around a DC bias point, then clearly your current is kind of nonlinear, right? The drain current versus gate voltage, if you look carefully, it's nonlinear. I've sketched it linear, but it's nonlinear. And then whenever you feed in a signal with a very characteristic frequency of omega, if it's a nonlinear output, then you will get multiple frequencies. So that's typically not desirable, in a linear amplifier. Basically, you want it may be useful for some other things, but for communications, it's kind of desirable to have a very linear amplifier. And I'm saying now that go back and see how can you. By the way, this is not I want you to kind of think about the problem that in the end, the GM and the drain current, they're all related to the band structure of this material that you're using, the electronic EK diagram and all that, the basic quantum aspect of it. And I'm saying that can you kind of see how can you make it more linear, what band structure may kind of give you that, and that sort of thing. So it's kind of, remember the inverse problem, we are saying we want this, what material should I choose now, right? So this. Okay, so and the rest are, and a few other problems on transport. I just wanted to kind of say, I'll talk about a couple of them here, but I also gave you a little longer problem, something that we started discussing last time, and this is, you can consider it as your kind of take-home prelim exam. We have a little more time to do it, but to be able to explain this plot, from all the transport calculation. So you are going to calculate these solid lines and get this curve as the end result of this problem. So you can, and this is what we are discussing at this point in time. I'll point out one more thing before we move forward with our discussion. This is a problem which is, I think some of you may have seen this earlier in some other courses, but it's a kind of a nice tunneling problem. Just saying that I have an electron sitting in kind of what you call as a quasi-bound state inside a quantum well, and there's a potential barrier, and the electron classically you can think of it as I asked you first to do it classically. Classically, if you have a certain kinetic energy, that means the particle is rattling back and forth, and there's a certain time or a frequency with which it collides with the wall classically, and you also know how to calculate the tunneling probability now from WKB, or just do your e to the power minus integral twice the evanescent wave vector inside here. So by combining these two, the attempt frequency of collision and the tunneling probability, you can calculate how long will it take for the electron to leak out of the well. You can get it pretty easily, So just think about it and then do that. And then as you change the voltage, if you change the voltage here, you pull the Fermi level of this side down, and then you have an electric field inside here, and now you are changing the area inside this exponential term, right? Tunneling probability to 2 times, I'll just write it down. So you have basically Vx integral, right? You have this thing. And from tunneling point A to B, the classical turning points. And this part is basically the area related to the area on the curve. It's kind of the square root of it, not exactly the area. But so you're changing the area, and that thing sits in the exponential. So this probability will change by a huge amount, with the small voltage. So meaning, like basically 10 to the power a large number, 20, something like that. And so you can change effectively you can change things by almost so something that may be occurring in, say, nanoseconds or milliseconds or even seconds to many years and something. So this is the basis for memory today, flash memory, which really revolutionized all the handheld devices, cell phones, and because you have low energy consumption and high density memory, which was earlier not possible with magnetic hard drives, but this sort of device made a lot of this impossible. Okay? So the idea is straightforward as far as classical intuition goes, but I just asked you to do the numbers here. But the third part, I'm kind of interested in seeing what you do. I've said that, well, this is kind of a semi-classical picture of how you deal with the memory. The third part, I've asked you to calculate the same time it takes for the electron to leak out, but by using the Fermi golden rule that we derived, or in the last couple of classes. Think about the problem a little bit. Essentially, you will have an initial state. Remember, the Fermi golden rule idea is, so I'm saying that you will recover the WKB result and all that from Fermi golden rule here. So it's a slightly different way of looking at the same problem. And in the golden rule calculations, we have said that if you want to go from initial state to final state, the rate at which that happens is so initial, and whatever potential is causing your scattering to final. So you find the matrix element, square it, and you have this energy conserving Dirac delta function, right? And so here you can, so you will be kind of spending a little time thinking about how to set up this matrix element for this problem. And the matrix element, just as a kind of a guideline, would be, if I just think of it as a potential problem like that. So the initial state looks something like this. Okay, so it's a quasi-bound state, and so if I were to plot my wave function, it would look something like that. But there will be some amount of leakage into this. There will be some amount of wave function that will leak into the finite barrier here. Yeah. This side you can assume infinite barrier, so there's this is 0. And then if you go out here, in fact, these are all allowed states on the right side. Does that make sense? I mean, this is an allowed energy, this is an allowed energy on the right side. Okay? So that means actually corresponding to this state here, there's also, meaning I'm going to just sketch it, the real part of the wave function looks something like that. Okay? This is very small, I don't want to kind of sketch it this way, but this is really the state that you, no, it's not going to oscillate inside here, sorry. Yeah. Something like that. Does that make sense? Okay. It'll die, but then there'll be a little bit left and it'll oscillate outside. And that part you know how to deal with. This is a free electron sort of picture. Based on the kinetic energy, you can write down its K and all that sort of thing, right? So you can think of this as your initial state is a quasi-bound state, and this whole thing, remember the wave function that you need for the initial state, psi initial, it's the whole thing. And then after it leaks out, the final state is such that the electron is only there, not here anymore, right? So, and so final state would be basically something that would be only on this side, but nothing would be left on this side. So you can think about how you want to set it up, but I mean, a simple way to do that is you can also artificially put a wall here and then take it to, it will cancel out in the end. Just like we put in volumes and lengths, and then we, you can see when you integrate over final states, the total rate you will have to sum over all final states, and it'll just go away. So think about how to do that, but I think it should be a good exercise. So you can think of this as some large L, and it's a normalization factor that will help you evaluate all your terms here, and you should get something very similar in terms of answers, meaning this way or that way. Not too. I mean, maybe if you are within even a order, a couple of orders, that's okay for me as far as this problem goes in terms of the numbers. Okay, so remember I had also for practice I had said that I'll ask you to do a problem where this, remember when we derived the Fermi-Golden rule, this was the first term in a series, right? Which is the kind of one scattering term, first scattering. Then you have the twice and thrice and so on. And so here's a, so I've asked you to kind of retain a couple of other terms and show a more general result. And then apply it to a case where the first term actually goes to 0. So there's no, because of symmetry and matrix element goes to 0. It's in a harmonic oscillator, and you have basically the problem here is you have a harmonic oscillator, and so the electron was sitting in the ground state of the harmonic oscillator, and first and second, and then at time t is equal to 0, you turn on a certain force. And just to be, I think also what it says, this is a force, not a potential. That means to find the potential, you must, force times distance is the potential. So multiply it by x. And when you do that and you find, initial state is 0 and final state is some other state n, you put your potential here, w of x, which is force times x, really. Right? You'll see that the transition, this term will basically vanish for all, for the first term, for all final states, it will just vanish. So, and, for the first excited state, meaning just to find it in states 0 to 1. Actually, can you see that from here? If this is x, why it should vanish, or from 0 to 1, maybe you can think about that, but it will go away, vanish, and then you have to look for the second term and all that. And this just asking you to look at the higher order scattering terms. Yeah.
Wait, is it because there are no degenerate energy levels? Can it only scatter into?
That's a good point. Actually, this is a very good question because you see, there are two things in this in the scattering rate calculation. There is a matrix element, right, and then there's the energy conservation term, right? Now, for scattering potentials that are time independent, remember, that cannot change the energy, right? But scattering potentials that are time dependent, like oscillating phonons or photons, or this one, if you look carefully, it has time, right? So this thing is basically a sharp, increase, and then it decays exponentially with time. Right? So it has time component, which means that it can change the energy, and it will. So it will change the energy. If it can't change the energy, then well, there's no scattering in this problem. It's completely ruled out. So in that sense, you can imagine if you didn't have the time part, or your tau was infinite here, this will be identically 0. And you can see that because your potential. Anyway, okay, so you can think about that a little bit. Yeah, sure.
So is that, so the example you gave, is that for the symmetry of state 1 and the node in the center of the wave function that you can't?
Yeah, it is definitely tied to the fact that the wave functions are one is even, the other is odd, and so on, right? It's and also the nature of the scattering term itself, right? So the three put together decide whether this is allowed or not. Absolutely, yeah. But so because you have also one of the very interesting things you can see here is if this was a e to the power I omega t, right, oscillating potential, then it will only kind of scatter to some preferential states, because it will, the electron will exchange energy. If it's e to the power I omega t, then you get like a plus minus h bar omega. So it has quanta. It cannot, easily go to any other state. For example. But here you have e to the power minus t by tau, and when you take a Fourier, it has all frequencies here. E to the power minus t by tau has all frequencies, so it is capable of scattering an electron from here to, in principle, to all states, but then the symmetries will dictate which states it actually scatters into. Right? So, yeah. Does it make sense? So it depends on the on the nature of the time dependence. Okay. All right. So we'll go back and look at a few cases of the. So today I wanted to cover. Also, I just want to kind of look at the page here. Where are we? And so I've started putting down in green the stuff that we have kind of talked about in the class, and I'm talking about golden rule and Boltzmann transport. So I'll talk a little bit about scattering, electron-phonon interactions, and such things right now. And we are slightly, maybe one lecture above the midway through the course, and we have the rest of the class to cover the other things we have I've mentioned here. Okay, so okay, good. So let's go back to what we were discussing in the last class. And yeah, question? Yeah.
I just want to confirm the prelim is non-clock.
The prelim exam, I would say, yeah, that the homeworks I encourage you to collaborate, but for the prelim, if you can do it by yourself and just talk to me if you have questions, that would be better. Okay, yeah. Okay. That's if you think would benefit, just let me ask me, and then I can suggest something also to in terms of talking to others. Okay, good. So what we were discussing in the last class was kind of removing this constraint of ballistic transport and saying that now I'm going to allow all kinds of scattering to occur. And if my electrons in any band, I sketch a parabolic band, for example, but it can be any band really that they find themselves in a crystal, and if I have states k with the energy Ek and states k prime, just labeling them like that, E of k prime. Right. So what we calculated in the last couple of classes is if I create a situation where the crystal potential deviates from its perfect periodic, ground state condition, then if the electron was moving through, and if it was in a perfectly periodic, atoms were all right, at their periodic locations wherever they're supposed to be in the lattice, then this is the full-blown quantum mechanical solution for all allowed energies of the electron inside the crystal. That's the basic result from solid-state physics. And now we are saying that we are introducing the possibility that there are defects, that there are phonons, there are all these perturbations to this perfect situation, right? And the way we are dealing with it is the following. We are saying that I still have mostly a perfect periodic crystal, but every now and then, there are maybe, these are maybe all charged neutral atoms, but there is one which is maybe a donor atom which has a charge in it, for example, right? Or there's an atom that's missing. There's a row of atoms that's missing, so that may be a dislocation, for example, a linear defect or a point defect, or I have, in principle, obviously the most interesting thing is even in a perfect crystal, all of the atoms are really vibrating, because of finite temperature, right? They're jiggling around, and that means, again, the lattice is deviating from a perfectly periodic potential, which gave you this band structure. Right? And that, whatever is the deviation from that periodic potential is what we are calling as our scattering potential, right? WR, T could be time dependent, could be time independent, right? So that's what we are calling as the perturbation here. If the perturbation is, this is something we discussed. If the perturbation is much smaller in magnitude than the periodic potential. Then all this stuff we derived on Fermi's golden rule and all tell us how, because now, just if we step back and think about it, these are not necessarily the eigenstates of the system anymore, right? Because the system has changed. It's not really a perfect crystal anymore. But because we are saying that we are in a very dilute limit, we are treating this in a way that the perturbation term that enters this was your original Hamiltonian, the potential term of the original Hamiltonian, right? Is p square by 2m plus v of x. This was your original Hamiltonian, but now we have added this as the perturbation term, right? And we solved the whole time-dependent Schrodinger equation, and we got the result that now, because of these defects, if I put an electron here at time t is equal to 0, or put an electron here at time t is equal to 0, there's a finite chance that it may leak out to other states, right? And that is the result that we wrote, derived in its approximation, being W k prime, right? E of k minus E of k prime. So this is the rate of scattering out. Yeah, there's a question.
So initially, the V of x would have the form. It would just be some potential energy surface describing the potential of your crystal.
Yeah, it's the potential due to the nuclei of the atoms and the electron clouds, and yeah.
Yeah, and then when you add the perturbation WRT, would those just be like? Would that just be like subtracting out whatever point defects you have? Would that just be subtracting out what, like numerically, would just be the energies of whatever atoms you're subtracting?
Absolutely. So, for example, let's draw a line along this row of atoms here, and the full-blown potential that the electron is seeing is looking something like. So and then here you have a charged defect, charged atom. A dopant, for example. So here are the rest of the atoms. Maybe these are all silicon atoms. That's a phosphorus atom, an extra electron. So the potential that the electron will see, the full-blown potential V of x, would be if you go close to the nucleus, right? It really the potential drops, something like that, and then comes back up, right? It's really varying by very large amounts, very large number of electron volts. So it's and then you have your nuclei sitting over here, and then the point here was because of this positive charge here. So if I look at it, so if I didn't have the positive charge, this would be a perfectly periodic potential, right? And this is what we are calling as let's call it V of x, and then this is your perfectly periodic potential, and because of the positive, right? Each of them has the same height and same shape. It repeats in every unit cell, right? But now, if I put a positive charge here, you can really see that there is, even classically, there is a little more chance that the electron will be somewhere around here. So the net potential will be modified in a way that maybe it will. I'm just exaggerating it, but it will have a little sort of average slope that will kind of bend downwards. So what we do when we talk about a band edge and we do effective mass theory, what we say is, well, the deepest states here are not really bound to the next atom. They are core electrons. These electrons are not shared. Then you go up, maybe another one which is core. Finally, you form bands. These electrons are the ones that can tunnel from one region to another, and they form bands now, right? Does that make sense? And so now, and when we sketch and then you reach up. So here's maybe a filled band, or rather, let's say this is an empty band, and then this one maybe it's a filled band. And what we are calling is this is the valence band. That's the conduction band, for example, right? Conduction band electrons can move because of the they have the electrons being wave-like particles. There's a certain probability that they can actually move across, and all that stuff is captured in the fact that we are using this effective mass picture with a very sharply defined conduction band and sharply defined valence band. And the conduction, I mean, in a perfect crystal, I would sketch the conduction band like that, valence band like that. This is what you call as, so effective mass picture tells you that all the details of microscopic, variations of the potential, of the real potential, are now taken into account if I found what is my electron conduction band edge, and all that details are buried inside the effective mass of the conduction band, right? So that takes into account all this periodic perturbation. So now I'm actually free to look at it as a very simple classical problem, almost, not necessarily fully classical, but with a EK diagram that is, h square k square over twice effective mass plus this conduction band. This is kinetic energy, this is potential energy now, right? Now, if I put a dopant or an impurity or something like that in this sort of a mean field or averaged or effective mass picture, what will happen is the conduction band will bend this way, and the whole thing will bend like that, right? And so the gap of the semiconductor does not change because of this thing, and so the valence band will also bend a little bit like that, and it's not so and the as a result, the electron will really be attracted to this point. If I plot it in 3 dimensions, it may look, in 3 dimensions, it's a Coulomb sort of well, it will look, like what you may, draw for a Coulomb well. So it will be a depression in 2 dimensions, for example, it will have this sort of a, depression. And so now the electron as a wave will obviously get scattered. Maybe if it's moving very fast, it may not be scattered much. If it's moving slowly, it may really scatter more and all that. The angle may change. So it's it has a very strong classical analogy too with the scattering sort of picture. But here's the full sort of picture. So the W is, you see this one, that's my W. Make sense? Whatever deviates from the perfect situation, whatever is the deviation. So. Okay, yeah. So what we are now trying to do is build up statistics, because typically the electron is not just in one state. We know that in K space, for example, for the ballistic transistor, for example, you saw that in 2-dimensional K space, the electrons were distributed in kx, ky's, right? And each of these modes had some occupation function, right? The source and drain, equilibrium, and all that. That was for ballistic situation, right? So if I allow scattering, and now what we are trying to find out is, I had written down the kx, ky for the ballistic situation by just saying that the right-going carriers share the same Fermi level as the source, and the left-going carriers with the drain, and so that locks their Fermi levels. And and once I put an electron inside any mode here, it stays in that mode till it gets out on the other side. Does that make sense? I mean, that's ballistic transport. There's no scattering allowed. But now what we are saying is that an electron that's going from the source to drain, maybe it's in this mode, because of these defects, these variations, it can scatter into another state, maybe here. It can scatter in another state there, and so on. We are allowing for mixing of the states now, right? So that is covered by this relation, and we are going to write this just as S k comma k prime. Just trying to avoid writing the whole expression for now. 1 over tau from k to k prime. Right? Yes, the scattering rate from k to k prime. Right? And we basically are going to have to look at the full-blown distribution function now. And we want to know what is f of kx, ky, because once we know that, I can go back to my full, expression for the current, which is in any dimensions, you sum over all k modes, and take your group velocity of that mode, and the current density is times the occupation function of that mode, which is what we are after, times the transmission probability if you have one. So this is your full-blown current expression. So really what we are, I'd also kind of emphasize in the beginning that a lot of transport, really, we're bothering about this most of the time, because all, the hard work of knowing the band structure and all is kind of done. The band structure information is here, but this is how you are controlling with the source, drain, defects, all of them enter here, not here. So, yeah. So transistor switching on off that we just talked about, all of that is from here, right? So the Fermi functions are changing, right? So occupation functions. So now we are looking at the equation, the Boltzmann equation, which tells us that once you have all sorts of scattering allowed, then how do you find your occupation function at any in occupation function for the this is very general. I'm saying it's for electrons, but this equation is really much more general than that. Okay, so I had discussed at least in the last class we had discussed briefly about how this equation comes about. It's from conserving basically conserving the particle number in a transport process. So if I have transport in the conduction band of a semiconductor or a metal or any material for that matter, if I have transport in the conduction band and I have a certain occupation function and I sum over all kx, ky's, right? So that gives me the number of electrons, right? If I just sum it overall. So what this Boltzmann transport equation is saying is that the number of electrons is fixed, and that's obviously a situation where you don't have electrons coming from other bands. That may happen, for example, when you have interband tunneling. An electron can tunnel from here to there. That's interband tunneling, in which case you just added one more electron to the conduction band, right? Or you can have light come in and this electron absorbs that photon and goes up, in which case you also add it. Those terms are called generation terms. And if you similarly lose electrons from here, maybe there are some holes here and the electrons went reduced, that is called a recombination. So so generation and recombination will lead to also aspects of current. For example, in a PN junction or solar cells, that part of the current is very, very important. Generation recombination currents. So here what we're looking at is, let's say the number is fixed initially, and in that case it's very clear that the occupation probability at any point in k and x of the electron, and these are the coordinates of the electron. You can see we're going into a classical regime now, saying that I know it's x and k. But then we know in the effective mass picture we have wave packets, so that the electrons are really spread out in a little bit in x and a little bit in k. So that's our constraint here. So this picture will be called kind of a semi-classical picture, where we are imagining that the electron is traversing this path in phase space, but this path is a well-defined path. It doesn't have spread in it, at this point. So you can think of it as the centroid, or the expectation value of this x and k at this point, for a quantum particle. And we are just tracking its flow of probability and saying that if the occupation of the probability of electron being found here in phase space x and k is f of x, k, and time t at time t, then at some point time in the past, the probability was x minus the velocity of the electron in real space, dx by dt times the advance in time, right? So that's x minus dx, k minus dk, and t minus dt. So the three variables and in real space, that's just velocity. That. All right. So we are saying that x, k, t is equal to minus dx, k minus dk, and t minus dt, right? And here, that would be the case if there was no incoming terms, and it's a ballistic sort of picture, no scattering. It's the ballistic limit. And then dx is basically velocity times dt, right? And dk, if you remember the quantum mechanical equation of motion, is F is h bar dk dt, right? For anything that has wave particle duality, this is the Newton's law. Force is h bar dk dt. So therefore, dk is just force over h bar dt, right? So you can just throw them in there, and you get that relation without the scattering terms. So force, yeah, right? And then we just say that we allow now, because this is still ballistic, and we allow now scattering in from other k states, just like I mentioned here. I'm allowing mixing of states from one k to another and all that. You have always a chance that a state, because of say scattering with the lattice or from a defect, it was at another k and it just it was at a k prime here and it entered this k, for example, right? So those are all the scattering events. So you can scatter into the state k, or you can scatter out of it. So we are saying scattering in minus scattering out. And these scattering is exactly what we talked about in the Fermi golden rule. This is the S. Right? This is S. This is the golden rule. And this is a rate. So to find the total probability, you must multiply by the time it took for you to do that, right? So this is 1 over time. Multiply by time. And in this point, this is a general relation. This is the total scattering in rate. This is the total scattering out rate. Total. Right? And Fermi's golden rule tells us for only one k state, one k to another k prime, just one, right? So to find the total, how would I write it? I will, for example, scattering in would require me to write it as 1 over tau from k prime to k, right? I'm filling state k. I'm tracking k state here. So I want to scatter in from some other state, and that's k prime. And for this to occur, for fermions, this is where we put in the Pauli exclusion principle. So for fermions, for an electron to scatter from state k prime into k, this must be occupied and this must be empty, right? Meaning not fully, but if k prime is not occupied, there's no, you can't scatter in from there, right? So meaning if k prime is 0, occupation of k prime is 0, then there's no chance for the electron to even start there, right? There's no electron there. Similarly, if final state is fully occupied, if f of k is 1, then you can't allow this to occur either. You can't fill with 2. So this is the way you weight it effectively. You can derive it rigorously from the occupation number and all that, but this is what you will get intuitively, and this is what you get from a rigorous derivation as well. So that would be, in fact, instead of writing 1 over tau, I'm going to still write it as S of k to k prime. That, I hope that's clear. I just that's a proxy for this whole thing. And minus, similarly, now you want to see the rate at which you are scattering out, and that would be you're starting from k and going out to other k prime states. For that, initial states should be occupied, final should be empty. So you get this relation that k prime, no, sorry. What did I do? Am I using arrows? I think it's better to use arrows. Okay, yeah. So this is scattering in, so k prime to k. And this is scattering out, k to k prime times f of k, 1 minus f of k prime. Okay, so that should be yeah. And this whole thing is, again, only for one k prime state. Do you see that? It's just for one other k prime state. But I want to add it for all possible other k prime states now. So I must sum it over all final k, all these states, right? So that's your total term there, the scattering term. So this is also called the collision integral in various terms, as a name. And so this is the ballistic part, and this is the scattering part of the transport process. Yeah. Okay, so now what we can do is look at this equation a little bit, and you can do a little Taylor series on this side, and write the differentials, you just expand around, pull out the x, k, and t, right? Say that this term, or the ballistic term here, is approximately equal to the t minus dx times del f over del x. Does that make sense what we are doing here? It's the first derivative, right? You pull this out. Right? Change due in space, change in k, del f over del k, right? And then there's a change in time. Sorry, just getting a new. So this term becomes just that, right? And then you have the whole collision term on the right side. Let's just write this whole big thing as a collision. C is an operator, if you want to think of it that way. It's just notation for it, the whole term here on the right side. So your new, once we do this Taylor series, you get this relation now, and then you can see that the original functions cancel out, and you get a differential equation in f, right? And that's okay. So the differential equation, and what we'll do is we just generalize it a little bit. Instead of writing it in one dimension, we can write it in higher dimensions, 3D, for example, and in which case okay. So the d over dx will become a gradient in real space, right? A gradient in real space of f. D over dk will become a gradient, but in k space, right? Gradient in k space of the distribution function, right? And the time derivative will stay. And by just doing this little manipulation, you can write the equation in this form now. That rate of change with time of the occupation function f plus a spatial gradient term plus a k gradient term is equal to the collision integral. This is a full-blown equation now. I think if you think about it, this is how it should be, because we have a phase space, so we have things can change in x direction or in k direction, right? So and then there's change in x, there's change in k of the occupation function. There are two derivatives, but now we are trying to associate with it some physical meaning, and that's what we want to do.
Yeah, I have a question. So on the board you have dx times df dx. So where do the differentials of dx, dk, and dt go? I'm just having.
Say that again. You mean this
So
equation?
you plugged in the gradient with respect to position of f and the gradient with respect to k space of f.
Yeah.
But what happened to the dk, dx, and dt?
Oh, they'll still stay. So okay, that's a good point. So so what we'll do now, maybe I'll just do one more step here. So you can write this whole thing. See, I skipped this part. So this whole thing times dt, right? And then you divide everywhere by the time differential. Right? So okay, and then you get dx by dt here, dk by dt here, right? And this dt goes away, and the dt goes away from there, right? And this becomes your velocity, and which will actually be a group velocity, and this becomes your force. F is h bar dk dt, right? Force, and that's no, that's the question. So that's what you
Okay, that makes sense.
Okay, yeah. Right. Okay. So now, so formally we are done with the problem. You just solve it and get the answer, right? And so here's the physics of it. So you have a crystal. The band structure. Once you know the band structure, you exactly know what is v of k for all k. This group velocity is just the slope or the gradient of the EK diagram, right? So based on how the atoms are placed, what are the symmetries of the atoms? It can be a metal, graphene, superconductor, whatever be it. It is determined already from the band structure. Now this depends on the gradient, so that this is something to be solved for. Force is something you're applying externally. Okay, this force does not include the force that the electron experiences because of the crystal potential. Does that make sense? This does not include it because that's already taken care of. This is any external force. You apply a voltage, with a source drain contact or a gate voltage, and you move the whole thing up and down. That's the force we're talking about, not the atomic force anymore. That's taken care of. Yeah.
I mean, obviously you can find an analytical solution for this, right? So like, do people use this for simulations and stuff, or?
Oh, absolutely.
So,
oh, yeah, absolutely. Yeah.
For transport.
Yeah, heavily, in fact, and we'll look at some analytical approximation solutions to it, but you don't have to. I mean, numerically, you can set it up and run and calculate your whole Boltzmann, distribution function based on this.
And as time t tends to infinity, would tend to the Fermi-Dirac distribution.
It's a good point. We'll discuss that now. Okay, we'll discuss that. Good point. Yeah. Right. So a few things. What do we know about this now? And what about the scattering rates? Also, completely determined once you tell it what are the defects, right? What are the defects? What are your W? What is the language you have to put in for saying what are the defects? You have to give it what is the W here, right? Maybe you have a scattering potential because of ionized impurities, which will not depend on time. Maybe you have acoustic phonons, which will depend on time, plus whatever. All these scattering potentials, club them together, right? And that will go into this. The microscopic details of all defects, everything goes inside here, right? And then once you put in the potential of the defect, this is completely determined as well, right? I mean, the scattering rate is just given a golden rule. I mean, you can't change it anymore. That's done, right? And then what's left is f of k, or f of k prime, but now you have a sum over f of kz, right? So it's a function that depends on, the value of the function here at this point in k-space depends on all other points in k-space. So it's what do you call, like a non-local thing, meaning it depends on all the other things as well. So it's a highly coupled system, if you might, right? So if you want to write it for every k state, you will see that you can think of it also as a matrix if you want. There's write this equation for every k1, k2, k3, and all that. So it's a highly coupled differential equation. Stuff that's happening here is feeding into the next one, and all that stuff. So they are strongly coupled through this equation. Yeah, there's a question.
So F, that force you added, that's dependent on the perturbation, though, right?
You mean this force? Yeah. So here's the deal. So the way it's the problem is set up is any the way we have formulated it here, if I apply an external electric field, that doesn't go here. That goes here. But it's actually a okay. So this is any deviation from periodicity. Okay. But then if I have maybe a defective crystal with potentials like this, then I'm only putting this on the right hand side. The F there is if I apply an external potential that bends the bands over the whole thing, that goes here. Yeah.
What if that external force now affects W of x?
Yeah, so those are interesting. So now you will get terms that can lead to, basically that will be the deviation from perturbation theory now. And that's, for example, field ionization. You will get very large change. Here's the deal. So most of these potentials will not, the change because of an external field, the external change in potential is very gradual. That's why we can treat it as a mean field, outside of this, and also it is right. So that's the primary reason why it's what we can deal it externally here. By the way, this can be rigorously defined, meaning over what range are we assuming the external forces to change, and if you can see that this will just not fly if my whole crystal is like 2 atoms. Then I can't really do this. It needs a certain number of atoms to work, right? And So this must change gradually, and all microscopic variations are buried inside in the collision term. Okay. So I think a good way to start thinking about it is, do we know some solutions? Yeah, Joe? Yeah.
Does the scattering term take into account the Fermi Dirac parts scattering into
Yeah.
states that are not allowed?
It's a good point. So this term is not, it's completely unaware of whether you are talking about fermions, bosons, Majorana stuff, doesn't care. This is just a scattering rate. What builds that in is the Fermi function here. This is what takes into account what is occupied and what is not occupied, this term here. Does this make sense? So this is just the, am I allowed to scatter? And if I'm allowed, is it easy? Is it hard? What is the rate? So this is the measure. And this is the source and the drain functions of scattering, meaning if you have any particles, it's here. If you can scatter into the other, it's here. So this, it kind of separates the two here. And so it also is very interesting if you look at it. This term is quantum mechanics. This term is thermodynamics. And Schrodinger equation has no thermodynamics in it. There's no Boltzmann constant. So this is a separation of the two. Sometimes one calls it a semi-classical theory because you are we can call it whatever. But so the quantum aspect of it is buried inside here, and this is the thermodynamic aspect of it. And good point. Yeah. So we'll see that if you can also solve this equation in what's called the Maxwell-Boltzmann approximation, which is the classical limit of the Fermi-Dirac distribution. Maxwell-Boltzmann distribution is when Fermi-Dirac distribution becomes exactly equal to the Bose-Einstein distribution, very large number of particles. So that's a classical limit, and you can solve it in that too. Yes, if you have, if you consider the full Fermi-Dirac, indeed we're building that in here, right? And the fact I've written it like this clearly means that I'm talking about fermions here, right? I mean, because bosons will not allow. I mean, you don't have to do this for bosons, right? So, yeah, it's true too. So, but if you want to do, for example, this is the distribution function for electrons. Now, electrons are going to dump a lot of energy into the phonon system, right? So you can write exactly the same equation, a Boltzmann transport equation for phonons. Look at the phonon k-space, right? And say, am I occupied, am I unoccupied? And there, the phonons can move. A phonon is a lattice vibration. It can move along the crystal, just like an electron moves, right? And a lattice vibration can, like a mass spring system, it can move. Now the phonons can also scatter. Phonons go there and they say, oh, there's a different mass here. So that can also scatter, a phonon wave. And so phonons can scatter, and they will have their own taus based on this, where everything will be now the wave function, or the function of the phonon, and these will be phonon Q states. And on the right side, you have now Bose-Einstein distributions, not Fermi-Dirac. So the collision term for the phonons. So you can have a hierarchy of these Boltzmann equations, and this is actually used in semiconductor design software today. Boltzmann equation, you can set it up and set up a k-space grid and let all kinds of scattering based on the doping you have and other things and temperature, and let it numerically solve, and you find out what is this. And if you are emitting into phonons, you can couple it to the phonon, because the electron and phonon system will be coupled now, and you can solve them together and see how much heating of the crystal happens by just tracking this throughout. But here's the deal. Very interestingly, we can say a lot of things without solving this problem, because the first thing we can say is, look, what if there is well, I don't apply any external field at all. Let's say I have no voltage applied, so this is 0. External forces are 0. And I have completely homogeneous crystal, metal, semiconductor, whatever be it, in which case there are, just by symmetry, there are no gradients in F anywhere, in real space either, right? And now I have an equation that looks very interesting. It says that the time derivative of the distribution function, if I want to find, I could have a 2D crystal, a 2D electron gas, and I have occupation function of each of these k states. And the equation is del F by del T is equal to, this whole integral of k to k prime all these terms that we have here, right? All k primes, right? So there's your equation for the simplest case where we have no fields, no gradients in the distribution function, and so that is equal to that, right? But now you look at it carefully, and it's very interesting saying that I have my distribution function that is, we have a time derivative, right? And if I have the thing sitting, the electrons distribution sitting and in the crystal and not being moved around by voltage or gradient, should it change in time, right? That's the question. So the distribution function f of k, should this be time dependent, right? If it's in what you call as equilibrium, if the electrons are in equilibrium with the lattice, then is it clear that this should be actually 0? Because it has there's no reason for f of k to change in time. I am not applying any forces, not applying any, it's not changing in time. But microscopically, what is going on, right? So electrons are still moving around. The moment I have a Fermi surface like that, these electrons are moving, these electrons are moving very fast. That electron is going in that direction really fast, right? There's an electron here moving very fast this way, and so on. Right? They're really moving. And if I have defects in their ways, if an electron moves along and there's a defect, there's also scattering going on right now. Right? Does that make sense? Scattering is going on right now. But in a way that because of all the scattering, because of the fact that electron is colliding with the crystal and all the scattering terms are really not 0. Scattering terms, this term and that term are not 0. Does that make sense? This is an important, really important result. But so microscopically, a lot of things are changing in time. Meaning electrons are moving. There's a distribution function. If I track the occupation function of that, it is really kind of doing a little change. The f of say k, f of k prime is doing a little change. K1, K2, K1, K3. Does that make sense? I'm just sketching the functions, the occupation values. They're fluctuating. Right? But the total occupation for the in a manner that these changes occur at the length of the scattering times, which are of the order of like 0.2, 0.3 picoseconds, or even lower than that. Right? The scattering events. But the whole effect of all this scattering is that the electrons the distribution function has reached a steady state. So there's, just like a DC current, if you look microscopically, there's some noise, right? But on a large time scale, it looks like they have reached steady state. And what is the distribution function at that steady state? So that's the question we ask, and what is the answer to that? Right? So we know there's this one we know. So if the electrons are in equilibrium with a lattice, and that lattice is, say, sitting on something that has a temperature T, right? Then the electron distribution is in equilibrium with the lattice. It is not giving it any more energy or getting more energy, but it's continuously doing that. It's exchanging energy between it, but it has reached equilibrium, and that means the electrons now are. This is the meaning of the Fermi-Dirac distribution, right? That the electrons have reached equilibrium with the lattice, and the distribution function looks, according to the Fermi-Dirac distribution, is E Fermi over Boltzmann constant times T. So this is the solution of the Boltzmann transport equation at equilibrium. Right? Actually, let me just say, we didn't solve for it. This came out from just considerations of the fact that the electron microscopically is scattering, it has reached in energy equilibrium with the lattice, and the fact that df by dt must be 0, and that means f of k is a constant with time now, right? And manifestly there is no time in this equation, right? So,
shouldn't it
yeah.
come out of this somehow?
Yeah, so Fermi-Dirac distribution can come, actually what I said just now from the point of view of scattering and all that is exactly how also it's derived. Also, if you look at it microscopically, you have an electron that is in equilibrium with a heat bath, and it has to. You get the partition function, and you sum it. It's exactly the same thing, really. Microscopically, is the same thing, really. Yeah. So when you can exchange energy freely with the lattice, you can get it from the exclusion principle and the partition function. Here we are just saying that we are invoking it. We are not deriving it from Boltzmann transport equation. Well, you can actually derive it as well. So, But okay, so that actually tells us something very interesting. By the way, so this picture is also kind of fascinating because I think there's also a very interesting connection to this is the steady state, right? Meaning a lot of things are happening, in every window, but if I go here or there, really nothing has changed for the whole object, right? But a lot of action is going on inside, right? And so this it comes from also. I mean, if you look at the story of the creation of the universe, right? There's a Big Bang theory, which is the prevalent theory now. I mean, and accepted. But there was also another theory called the steady state theory, which was competing when it came along, and that had to do with creation of matter and antimatter in many places, and then recombination, and it happens all the time. So that says that universe is not expanding, for example. This sort of picture also comes from, has a very close analogy to that. That lot of microscopic details are hidden behind the fact that we are, saying steady state. Steady state here, equilibrium and steady state are the same, right? But I can pull the system out of steady state. So I can pull the system out of equilibrium, right? But I'll still reach steady state. And that I can do very easily by applying electric field now, right? Applying electric field, and my Fermi-Dirac distribution was like that, and that was equilibrium steady state, right? Now I apply electric field, and maybe I have more carriers going to the right, a little less going to the left. But given enough time, that also reaches steady state, right? So what will happen is, if I'm tracking the state here, that state occupation function maybe was very low, and then it went up, right? And then it'll kind of, it'll maybe oscillate, do something, but it'll reach steady state again, right? So equilibrium and steady state are slightly different. And here, what the equation is really telling you is at equilibrium, steady state, both, the scattering term microscopically must be 0, meaning this is equal to that for all k and all k prime. And if you violate that, you actually will have a problem with the energy of the system, and momentum of the system will be violated if you violate that. So this is microscopic irreversibility, if you might. So this term and that term must be exactly the same. And this is saying something about the scattering events now. You're asking a few times that does the scattering event take care of the fact that these electrons or photons or bosons or fermions. So scattering rate, I mentioned a few times, does not care at all about whether the state is a fermion or a boson, but it does care a little bit about the energy of the state. And from this relation, it may seem, from Fermi's golden rule relation, it may seem that whether you're going from k to k prime or k prime to k, it's irrelevant. It looks like the same. But I think you can very well see that as far as energy cost goes, going from a lower state in energy to a higher state in energy will be harder, right? This is more difficult than that from the energy, because the system wants to minimize its energy, and in the end, this is going to be a little bit easier than that one, right? And how do we take that into account? So if you just invoke this relation now that at steady state, equilibrium, these two terms are the same, then, and the fact that both of these f of k prime and f of k are the Fermi-Dirac distribution functions, right? This are the equilibrium distribution function. For electrons, it is the Fermi-Dirac distribution. If you go to phonons, it will be the Bose-Einstein distribution. But anyway, regardless, so here is the Fermi-Dirac distribution. And so now you can see that scattering rate from k prime to k times Fermi-Dirac distribution of energy k prime, 1 minus this, will be related to the reverse process from k to k prime. And these are the Fermi-Dirac functions. And if you take the ratio of these two now, and Fermi functions are simple, right? You can just use this, and you have two energies, Ek and Ek prime, right? Two energies in this relation, and you end up getting that the rate from k prime to k is related as e to the power this energy difference over kt. Right? So there's a penalty in going up in energy, and this is so basically it's saying that the okay, just to repeat again, this process is e to the power minus the energy difference, right? Ek over kbt, right? So that's how this process. Okay. Yeah.
We're a little bit over.
Oh, I see.
Go to the next class.
Okay, good. So I see it's 10 o'clock. So let's finish this today, and we'll continue on Thursday. Okay, so right, yes.